All right, now let's take a look at the table that comes after the example 2 in our notes. So in this table, we are going to fill in antiderivatives of some common functions. So some of the work that we did in example 2 will help give us some intuition and insight to what these antiderivatives should be. And so let's just take a moment to recap. So what is an antiderivative? Well, an antiderivative, let's call it big F function, is a function such that, so we'd say more specifically antiderivative f of x of a little function f of x is a function such that the derivative of big F with respect to x is equal to little f. So we want to know what function has the derivative of the little f function given. So let's first take a look at x to the n, so this power function. So what we saw in example 2, several parts, we saw these power functions come up, and we had to find an antiderivative. So an antiderivative here, we want a function whose derivative is x to the n, then the exponent has to be 1 larger than the exponent we want, and we have to divide by that power n plus 1 in order for n plus 1 to cancel when we take that derivative and move it out front. So let's just do a quick check. I'll make this a little more clear here. X to the n plus 1 divided by n plus 1. So let's do a check. How would we check? Let's clear some room for ourselves. Well, let's check. Let's take the derivative of x to the n plus 1 over n plus 1 with respect to x. So here the power comes down, n plus 1, x, we remove 1 for the power, so we just get x to the n, and then we're dividing by that constant n plus 1. So the n plus 1's cancel, and we get that function we want, x to the n. All right, now let's take a look at this next one. So this antiderivative works fine for almost all n, but recall, what if n is equal to -1? If n was equal to -1, and when we add 1 here, we get x to the 0, which is 1. And in this case, the derivative of 1 is equal to 0. Derivative of a constant is always 0. So we don't get the correct antiderivative here. So we need to make a special note. This is for n not equal to -1. So what happens when n does equal -1? All right, so that means our function x to the -1, that's equal to 1 over x. So let's recall, what function has a derivative of 1 over x? So you might recall that we see that behavior for the natural log function, ln of x. One thing we need to be careful about here, though, is x to the -1, or 1 over x. This works for all x that are not equal to 0. Does ln of x work for all x? Well, let's take a look at what this natural log function looks like, just to recall the shape and behavior of that graph. I'm going to go over and use my Desmos graphing calculator, and I'm going to type in my function ln of x. All right, here we have it. So what do we notice about this graph? What are the possible x values we can input into this graph? We will see that we can input any positive x value. So we cannot plug in any negative values. So when we write ln of x as the antiderivative of x to the -1, we need to add a detail here. We need to make it clear that we can only take in positive x's. So we're going to put absolute value around that x. And we can see why this should be true. So let's do a little proof over here, explanation. So the function ln of x, absolute value of x, is equal to ln of x if x is bigger than 0, and ln of -x if x is already negative. So if x is negative, then taking the negative of x gives us a positive value. So the ln of the absolute value of x is actually what's called this piecewise function. Okay, so what does this mean in terms of the derivative? Well, that means the derivative of ln of absolute value of x is equal to the derivative of ln of x if, again, x is bigger than 0, and is equal to ln of negative x if x is less than 0. So we can continue with this. Derivative of ln of x, we know, is equal to 1 over x if x is bigger than 0, and derivative of ln of negative x is equal to 1 over negative x times negative 1. So this uses the chain rule. So we're taking the derivative of ln with respect to that inside function, and then we take the derivative of the inside function. Derivative of negative x is negative 1. So this becomes 1 over x if x is less than 0. So either situation for what x is now, if it's positive or negative, the derivative of ln of absolute value of x is 1 over x, which is what we were trying to find. The function whose derivative is equal to 1 over x. All right, so let's keep going, looking at the rest of these. They start to get easier. So we saw in the example 2 that sine of x is an antiderivative of cosine, because the derivative of sine is cosine. And then we see that negative cosine of x is equal to positive, or the antiderivative of positive sine is negative cosine of x. And that's because the derivative of cosine is negative sine. So if we want to find an antiderivative for positive sine, we need to negate that cosine. E to the x is a fun one. Derivative of e to the x is e to the x. So the antiderivative then is also itself. And now if we have k is just some constant, well, what function has a derivative that's just a constant? Well, it would be that constant times x. K times x, derivative is just k, which is what we are looking for. And now here are 2 more that we're not going to work out in this class, but you can just use it when you're looking for integrals or antiderivatives. So we have the function 1 over 1 plus x squared. The derivative here is antiderivative is arctangent of x. And recall this is one antiderivative. If we added a c to this, a constant, the derivative would give us the same thing. And then we have our final row here, and that is the function 1 over square root of 1 minus x squared. And antiderivative here is arc sine of x. So if you would like to see more details on these last 2 formulas, and you were in one of my classes last quarter, I'd like to refer you to one of our sections where we looked at trig derivatives, or derivative of trig functions. In particular, we looked at these functions in section 2.6 of our notes on derivatives of inverse functions. What we did in that section was we started with arctan and arcsine. From those, we computed the derivatives, and these were the functions we got. So now we can use that information for us this quarter to determine what those antiderivatives of the original of these functions are, based on that work that we did finding the derivatives of these functions. Awesome. All right, great work filling in this table. Make sure you have it all clear. It's going to be a very helpful table that you can refer back to when you're looking for antiderivatives, solving some of these problems ahead in our lectures and in our homework.